Good morning or good afternoon, wherever you are. I'm Doug Hooton, professor at the University of Toronto in Canada. It's my pleasure to be here today and talking about reducing carbon footprint of concrete mixtures using existing tools. So I'm going to talk about current global impacts of cement and concrete, methods that can be used simultaneously to reduce those impacts, as well as improving concrete durability. They will include things that reduce the cement paste content of concrete and also reducing the clinker content of the cement in that paste fraction. So what are the emissions? Concrete is a sustainable building material. Of all the materials available, it has the lowest embodied carbon and energy footprint of any construction material on a mass basis. It uses local materials, and if it's properly designed and executed, has a long service life and can be recycled at the end of the life. But we can do things better by making a few simple changes. In this graph, a graph from the University of Bath, shows the embodied CO2 on the vertical axis and embodied energy on the x-axis, and shows that concrete is at the lowest end of that, both scales. These are log scales. See, cement's up higher, but cement's just a component within the concrete. You see that other materials such as glass and plastics and steel are way up the scale. So the issue is that we use 20 billion tons of concrete a year. So that global impact is large. About 7% of global CO2, man-made CO2, and energy, about 4% of energy is due to cement and concrete. But it's not uniformly distributed around the earth. The developed countries typically have lower CO2 emissions because they're not building as much. The US EPA, Environmental Protection Agency, shows that the cement industry is only using about 1.25% of total US industrial emissions. The reason is that other countries, China is the largest producer of cement, followed by India, and then other developing countries in Africa and Asia are using most of the cement. The industrial countries at the bottom there are not using much cement anymore. So we've got to work to do this, make these changes around the world. And the reason for this is that Portland cement is the primary binder in concrete. It's manufactured from limestone and shale or clay, fired at high temperatures to form cement clinker, which is then crushed to the powder. But 2/3 or 3/4 of the material is calcium carbonate, limestone. And when you heat to about 800 degrees, it breaks down into calcium oxide and gives off CO2 to the atmosphere. And that's unavoidable if we're going to have calcium silicate cements. The rest of that, that's about 60% of the emissions. About 40% is related to fuel, to fire the kiln, and energy to turn the ball mills. But cement is only one ingredient of concrete, but it has a big impact on the emissions associated with concrete. If you just take plain Portland cement concrete, this is US data from some years ago, shows that about 96% of the total CO2, embodied CO2 in concrete, is from the cement. About 85% of the embodied energy is also from the cement. But the industry is improving its performance with carbon footprint or global warming potential, and has shown since 2014 21% drop in that carbon footprint. And that's based on industry-wide environmental product declarations, EPDs, over the whole United States. And so it's documented by third parties that those numbers in 2014, 19, and 21 are real. And they're largely due to increased use of supplementary cementitious materials replacing cement. As time goes on, the US is just starting to adopt more Portland limestone cements. So I expect to see in the next few years even a bigger reduction. Now, the industry is working to around the world to develop emission cutting roadmaps, as shown. This is the PCA one shown in the cover. The aim is to try and reduce CO2 emissions by about 40% in this decade by 2030, and go to net carbon neutrality by 2050. And that's going to require a lot of other work. But the things I'm going to talk about today should help us get to 2030. And then be more efforts on things like carbon capture and sequestration and other types of non-CO2 emitting fuels that will drive the 2050. And this is data showing courtesy of Karen Scrivener from a paper that was published a few years ago, showing that from 1990 standards, the cement clinker content was about, on the left-hand graph, about 0.84, and it's steadily going down as time goes on. It's down in the 0.7475 range now. Is that percent clinker in percent of cement of the total cement, and it shows the CO2 emissions associated with cement have gone down linearly with that reduction. But concrete, on the other hand, independent of the clinker factor, seems to be using a lot more, more highly carbon intensive than you could do by optimizing the mix. And that's all the data is above that line. So what can we do? The government and industry recognizes the need to reduce the global footprint, to reduce the global warming. There's been a lot of research by a lot of people on all kinds of different things to try and do that, including a lot of innovative new materials, non-calcium based materials. But a lot of these alternatives aren't going to replace the large volume of concrete needed. Portland cement will still be part of this story for a long time because of the sheer volume of concrete we need. The other thing is that a lot of these green, so-called green cements are not been independently evaluated by third-party environmental product declarations. So it's hard to know what if the claims are justified. But we have simple things we can do now, and that's what I'll talk about. But in spite of the fact that there are simple things, and they're certainly allowed in standards, there are still roadblocks to implementing simple, well-known methods. And if we can't overcome the roadblocks in the construction industry to using those things, what are the chances of implementing non-standard materials that are further down the line? So what can we do? So we've got 4 options that I'm going to talk about. Optimizing total aggregate gradations, and that'll help reduce the cement paste fraction by maximizing the aggregate content. And that is enabled by using water reducing and superplasticizing admixtures that allows us to do that while keeping the water content low to make workable concrete. And we can change the type of binders. So we can use Portland cement. Portland limestone cement saves us about 10% CO2 over normal Portland cement, at least in the American market. In Europe, it's even more with the CEM2ALs. It's about almost 20%. We can increase the level of supplementary cementitious materials, either separately or in blended cement, and reduce that even further. And we can do all of these things together, and the cumulative benefit is quite large. So if we're going to optimize aggregates, the first thing we want to do is maximize the largest feasible aggregate size, given any limitations on rebar spacing and cover spacing that would allow the concrete to flow around those spaces. A lot of companies only supply 20 or 25 millimeter max aggregate sizes, and they may not have larger sizes available, so we may be limited to that. But we can reduce paste content by using combined aggregate gradations. Having to meet separate gradation limits for fine aggregate and coarse aggregate results in a gap graded mixture, and we end up wasting material. A lot of material, especially with quarry operations, crushed stone, waste a lot of the small pieces that get ground too fine in the crushers, and then that can't be used for concrete aggregate. So it ends up being used for lower quality uses. You can also use microfine fillers to fill in the fine end. That's typically something we do to reduce the cement content for ultra high performance or self-consolidating concrete that may have high powder requirements, but a lot of that cement doesn't hydrate, so it's a waste of cement. Now, we all know that packing small particles between big particles will occupy more volume and reduce the amount of paste or water, in this case, in this diagram, needed to fill the voids between those particles. But you can't optimize aggregate packing using only 2 materials. And here's a typical gradation used in North America for this fine aggregate in blue here, the envelope, and it falls in the envelope real good. And if in the gold, here is the coarse aggregate envelope. But when you put them together, we end up with a gap in the middle, which I'll show you in a minute. And these things were developed over 100 years ago before we had chemical admixtures. So if you wanted workable concrete, the gap was somewhat necessary, but now we can optimize gradations using chemical admixtures and get more aggregate in and make workable concrete. So if you only have sand and stone here, you end up with a gap graded mixture. We have more paste requirement. If we can put some sort of material like that mid-sized material, the stuff that was too fine for the crusher, from the crusher, or other materials that fit in that gradation in the middle, we can fill in that gap and reduce the volume of the void content, reduce the paste fraction. And if we do that, we can get improved product performance, such as reduced permeability because we get less paste. The flow of aggressive fluids is through the paste fraction, not through the aggregates. And similarly, volume change characteristics like shrinkage and creep are related to the cement paste fraction. So if we reduce that, we can reduce those properties as well, or those expansions and contractions. Now, there's different ways to get there. One way is to try and fill in that void. So that blue line shows a fine aggregate on the left, a coarse aggregate on the right, and a gap in the middle. So it's down low. What you would prefer for optimized gradation is what they call a haystack, or a red line. So it's up in the middle. So we need something in the middle to fill in that space. And one way to get there for lower workability concretes like pavements has been developed in the United States using a guy named Shilstone, who developed this, and he developed the 818 curve, which means no more than 18% of the material aggregate should be on any one sieve and no less than 8. So it should be in that range. So it's in the red shows that, the blue falls out of it. And this coarseness factor is the percent fine aggregate versus the percent of coarse aggregate over the total coarse and intermediate aggregate. We want to be in that box in the middle where it says optimum. But a way you can use to model this, and it's a simple spreadsheet calculation, is to use the power curve. It was originally done by almost 100 years ago by Fuller, and other people have worked on it. You're basically looking at the percent retained on each sieve size, the percent as a function of the maximum size raised to a power n. And Fuller worked on n was 0.5, so square root. But in practice, that's too high and depends on particle shape and texture and the desired slump. So typically, normal low slump concretes would use 0.4 to 0.45. But if you want really high slump concretes like self-consolidating concrete, you need to be much lower with the n, 0.25 to 0.3. And even the fine materials can be counted in the sieve size range. I'll show you a diagram here. This is a project. We've got the smallest particles are the cement grains down at the bottom here on the lower left, going up to the coarsest particles on the upper right of the aggregate, and you've the percentage of the material relative to the size and the cumulative percent passing should fall in a straight line. So the optimum curve is the black straight line there. The dotted lines give you some leeway either side of that. And the red line here is 3 aggregates together, a 25 millimeter aggregate, a manufactured sand, and a mid-sized material in the 3 to 7 millimeter range. And we can fit it pretty well, except down at the low end here, because the manufactured sand doesn't have a lot of fines. But we can make self-consolidating concrete with this, fairly high strength self-consolidating concrete with that power factor of about 0.25 to 0.3. And some examples, one of my students did work on this some 10 years ago. We were making 50 MPa mixes that had to meet a permeability limit. And by optimizing aggregations, just using a mid-sized material between the sand and stone, we could reduce binder contents by 16%, while maintaining the strength and permeability limits and making workable concrete. With 35 MPa mixes, we were able to get about an 8% binder reduction and still meeting the permeability requirement for that. These are both used for chloride exposures. So we use the same material as the coarse aggregate, just finer sizes that would normally be wasted, and we saved a lot of cement. And here's that 35 MPa example showing this the 30 kgs per cubic meter reduction in cementitious materials. And then we added the screenings, as they're called, the mid-sized material. About the same amount of mid-range water reducers. Strength went up by 11 MPa. The shrinkage went down by 24%. Permeability, as measured by the Coulombs test, ASTM C157, went down by 28%. And of course, this is achievable because we have water-reducing admixtures to allow us to obtain this workability. But all concrete should have a water-reducing admixture of some sort in it, because this picture on the left shows cement grains in water. And cement grains tend to flocculate in water because of surface charges. You get clumps of cement grains in areas with no cement grains. And if that hardens like that, you're going to have areas of high water cement ratio, areas of low water cement ratio. On the right, if you put surfactant in a water reducing admixture, you get deflocculated clumps of grains, so they're independently separated, so you get pretty constant water cement ratio when they harden. So, okay, now we're going to play with the cementing materials. We can do different things. We can replace part of the cement with supplementary cementitious materials, fly ash, slag, silica fume, or natural pozzolans. And we can put limestone in the cement, intergrinding with the cement. And these are just the American designations. Type 1L is 15% limestone, as opposed to straight Portland. And this is in Europe. EN 197 has limestone cements with up to 20% limestone, the SEM 2ALs, and up to 35% limestone and SEM 2BLs. And it also has, the EN 197 has blended cements with slag and fly ash and other materials as well. Many types of cement are possible with the EN 197. In North America, we tend not to use blended cements, and there's historical reasons for that. I won't talk about that today. A few exceptions to that is the new introduction of limestone cements with up to 15% limestone is covered under the blended cement specification. So it's Portland limestone cement. And in Canada, the other only exception we have is silica fume blended cement, because silica fumes can be difficult to handle. And so all the companies in Canada make a blended cement with about 7 or 8% silica fume in it. And then at the ready mix plant, they would add fly ash or slag to that combination for various purposes, like high strength concrete for high rise construction or for high chloride resistance. So the Portland limestone cements are covered under various standards in Canada and the United States. For the North American approach, they were designed to give equal performance to type 1 or normal Portland cement. So equal performance, equal setting times, equal strength development at early ages. So it should be plug and play. You should be able to take out type 1 cement and put in type 1L cement, and nobody should know the difference. So that was the whole approach with this thing, to not make a second-rate cement, but make a cement that behaves the same. So the only real differences, if you read the specifics, the mill certs are the loss and ignition limits are higher because of the limestone that's in there. Will lose mass when it's heated in a furnace. And the plane fineness, the surface area of 1L cements will be higher because the limestone is softer than the clinker. So when you grind it, the limestone grinds preferentially. We want to get equal clinker fineness, so they grind to the same 45 micron residue to get the clinker fine enough so you get equal performance. And these cements perform really well with slag or fly ash at normal replacement levels, so the ready mix companies don't have to cut back on any SCM levels they're using now. In fact, sometimes they perform much better. We've certainly seen that in Toronto, in ready mix market. Now this graph was developed by Thomas Matchai and with Duncan Herford some years ago. They shows change in strength in red here, based on mortar cubes, and in calculated porosity in the orange diamonds. And the starting point is 0, so at 0% limestone, we're starting at the 0 change in performance. When we add 2 or 3% limestone, the strengths went up by 10%, and the porosity went down, as you'd expect. As you add more there, more limestone, the strength started to come back down, but by the time it got back to the neutral place, it was out about 12, 13% limestone to be as good as 0 limestone. And the porosities are about the same. Now, we're also going to use supplementary cementitious materials to replace cement, Portland cement component of concrete. And that can, as like I said, it can be blended cement or can be added as a separate ingredient to concrete. They work well with Portland limestone cements. And so if we add them together, and this shows that similar graph I just showed recently, this is work by Jason Weiss and his students at Oregon State University, showing that when we add percent limestone on the x-axis and just measuring porosity now, the porosity goes down even further if we add alumina to the system through fly ash, slag, kaolin, metakaolin to the concrete. We can get more aluminates will react with the calcium carbonate, forming carboaluminates, and we can bring that porosity down even lower, which means we can go to higher limestone contents and still get better, lower porosities, higher strength than we would have otherwise. So there's a real synergy with between limestone and alumina-bearing SCMs. And it shows some examples from concrete work I was involved with, where we take straight type 1, our Portland cement, which is GU in Canada, has typically about 90% clinker, and we make concretes at 0.40, and we see strengths at 4 different ages here. If we put 40% slag in, we can cut the binder to 53%. We see some reduction in 7-day strengths. The 28-day strengths are equal. But if we put limestone in there, limestone cement and 40% slag, we reduce the clinker factor even further, and the 7-day strengths come back up. So there's a synergistic reaction between the limestone and the aluminum and the slag, gives us increased strength at early ages, and we get better strength right down the line at later ages, and allow us to even add more slag to get similar performance. If we want really high performance, we'd add silica fume and slag together, which is typically what the type of mix we would use for high rise in Toronto with the limestone cement. We're still cutting the clinker in half, and we're getting even higher strengths at all ages. And on the same mixes, we see that the permeability index, as indicated by the 1202 Coulomb test, is much reduced by the slag, or the slag and silica fume in this case, over Portland cement. So Portland cements typically have a different pore structure. They're going to be higher in these values. And this, what the big benefit here is from the slag, but you can see when we add limestone with the 40% slag, it drops another 50 to 100 coulombs across that range just from the limestone. So that we are reducing the permeability even further. Now, supplementary materials aren't all available in any area. Like I said, in Ontario, where I live, blast furnace slag cement is the common supplementary material. We don't have power fly ash anymore. But in other areas, out in Western Canada, Western US, it's mainly fly ash. Other areas of the world, it's a natural pozzolans. We allow ground glass pozzolans now in the North American standards. Karen Scrivener is talking about LC3, which is a limestone calcine clay mixtures. So all these things can be used, but you have to use what's available, because there's no point transporting materials 1,000 kilometers, because that's not sustainable either. Now, this is just some data showing if you take straight Portland cement, 91% clinker in this example, make the 15% limestone cement, GUL, we get down to 81%. We can add 25% fly ash, we're down to 61%. If we put 50% slag replacement instead of the fly ash, we can get down clinker content about 41% of the original. And that means we're reducing the CO2 emissions by about the same values. Okay, so what about the sustainability? Well, the levers, how does it affect durability? So this is drying shrinkage. There's some mixes here. In the left-hand boxes, we have Portland cement and then Portland limestone cements, showing no difference in shrinkage. And when we put slag in there, we actually get reductions in shrinkage, and there's no effect of the limestone on that. So the slag in this case is reducing shrinkage. The limestone is not having any negative impact on the shrinkage, certainly at early ages. ASR, the two curves at the bottom are Portland cement with 25% fly or with fly ash, different replacement levels, versus Portland limestone cement and fly ash. And you see it didn't affect the amount of fly ash needed to mitigate to the concrete prisms to less than 0.04% expansion at 2 years, which is our criteria. And with Portland, with 50%, sorry, with different amounts of slag, the differences were very small, about 5%. It turns out the limestone cement needed less slag to get down to that level of 0.04. And same with freeze-thaw resistance. All these yellow bars are Portland limestone cements. The blue bars are Portland cements at different water binder ratios, and also with slag and with fly ash. And there's no difference in freeze-thaw performance. The scaling performance is not affected by the limestone. But although the numbers on the right are higher, they're still well within acceptable limits. And largely the higher values with SCMs here are an artifact of the specific scaling test of ASTM. They don't allow for the different finishing times and the different curing times required for these materials. So therefore, they always perform worse in the lab tests, but they don't perform worse in the field. Again, this rapid chloride permeability index test, the limestone is not having a negative impact on the results. And you can see the big influence of fly ash and slag in reducing those values. Carbonation. I did natural carbonation tests for 7 years at 50% relative humidity and room temperature. And it shows with one mix on the left-hand graph, trial mixture with 15% slag and with and without limestone, there's no difference in the rate of carbonation, the limestone cements. The lower right graph are some mixes. The top two mixes, the pink and the blue, are with 25% slag. The bottom mixes are the straight cement or Portland limestone cement, and the green one has the lowest carbonation rate is the Portland limestone cement. These are all at the same water binder ratio. We looked at sulfate resistance. Michael Thomas and I did work on a long-term. We set thousands of beams out in 2010 in severe sulfate exposures, and we'll be monitoring them again this year after 12 years. But we wrote this report in 2016, which is you can download for free from the Portland Cement Association. What we found was there's no negative effect of limestone on sulfate resistance when you make sulfate resistant systems. So if you use fly ash slag to get there, there's no difference in the way the 1L or the straight 1 cements work. In fact, these mixtures with type 1 or normal Portland cement and with or without limestone and SCMs are outperforming purpose-built sulfate-resistant Portland cements. Here's an example of some trials we did early on. I got our highway department back in 2009 doing their very first trial. We did several trials, but this is the first one. And what we found was with and without limestone, with a small amount of slag, got the same drying shrinkage, very similar strength characteristics at all ages, same freeze-thaw performance, the same mass loss in Deicer scaling, but we got reduced permeability by this chloride index. Now, people worry when we get too high on the supplementary cementing materials, not so much with silica fume and metaculum because they're much more reactive, but with low calcium fly ashes and to some extent slag, you can get slower early age strength development. So that requires redesigning the mix a little bit if necessary to compensate for that. The other thing is, of course, if you warm the concrete or you cast in warm weather, high SCM mixes can take off, they can accelerate the reaction. They're more sensitive to temperature than Portland cements. And you get much higher strengths in situ than you would expect based on testing small lab specimens at constant temperature. And the other thing is there's nothing magic about 28 days. Silica fume is great. It reduces permeability, and this is a log scale of age and Coulomb values. You get low permeabilities, about an order of magnitude lower with 7% silica fume, but the slope of reduction with age is small because it reacts quickly, just like Portland cement. It's about the same slope. But if we take fly ash at 28 days, it doesn't look any better than the Portland cement. But by a year, it's almost as good as the silica fume. Give it another year, it'd probably be as good as the silica fume. So it depends on when you need it. When do you need that permeability? When is the structure going to be open? And you're building something for 50 or 100 years. How important is that first half a year or a year in the life of the structure? Okay, so what are the barriers to these simple things? The barriers, some of them involve specifiers don't like change. Most people don't like change. They're doing what they've always done, and they like to do it that way. But something like Portland limestone cement, which should be plug and play, and nobody should know the difference, the producer or the contractors. But after 10 years in the United States, there's still a lot of specifiers that will not specify it. And the number of states is growing. This is as of last November when California finally adopted it. They're one of the last adopters of new technologies. They funded a lot of work at Oregon State University that convinced them that it wasn't doing any harm to them. And so if we can't get something simple like Portland limestone cement where there's almost no imperceptible effects on the outcome, what chance do we have of moving more complicated innovations? This is just a history in North America. What do the specs allow? We have performance specs in Canada. We have adopted Portland limestone cements in 2008, 2012 in the US. Ground glass pozzolans are approved as a new material. We allow high supplementary cementing materials ratios. We allow optimized total aggregate gradations. And we've recently allowed in Canada the use of harvested landfilled coal ash for use as just regular fly ash. If they process it, they can use it. Even if there's bottom ash mixed in it, they can grind it and make fly ash out of it. We call it fly ash. And the reason is all the coal plants have shut down, but we've got hundreds of millions of tons of buried fly ash that just didn't have a use. And in the US, it's over 1 billion tons sitting around in 500 deposits around the United States. And they're now balloting at the ASTM to allow that same thing. The other thing that prevents us from moving forward is the lack of use of performance specifications. If you know what you want, you define the performance, not just strength, but other values, permeability, shrinkage, whatever performance you need. But some specifiers still want to prescribe things like minimum cement content. So they want to prescribe the slump. And that leads to all kinds of problems on a job site when the specifier is trying to tell the producer and contractor how to do their job. And it just leads to problems, either adding water on site or making less sustainable mixes. Some specifiers are still using outdated codes and standards. They just haven't upgraded their standards. So even though the standards are there and they've been changed, they don't necessarily take advantage of them. I've seen 30-year-old standards being used on current projects. And so it's really unprofessional. We need to, the other big barriers are education. Design professionals and specifiers need to be educated because things have changed. And when they went to school 20 or 30 years ago, they didn't talk about sustainability very much. So they need to get informed about what's going on. So we need tech transfer to help them. And we also need on new jobs, we're going to try things for the first time where people are nervous. People promoting this need to provide tech support on the ground for early adopters. But the information and education is needed all the way down the food chain. So contractors and even their construction workforces don't like change because it's different than what they're used to. So you need to explain it to them. What's different about it, or if anything's going to be different about it. Because even small differences can throw people off. When self-consolidating concrete was brought in to save time and reduce vibration, then we had form blowouts all the time because people didn't realize they had to redesign the formwork for these higher formwork pressures. When silica fume was introduced, the lack of bleed water resulted in finishing problems and plastic shrinkage crack. We now know how to deal with that. And so Portland limestone cement, for example, may feel different, where the timing for high SCM mixes in terms of finishing may be more sensitive to concrete temperature and the amount of SCMs. So that they need to be, as long as they know how to do things, they can do it. But when they don't know, it's a problem. And the other barrier we have is supply chain issues. A lot of concrete plants don't have extra silos for adding new cements. So they either have to not use it or completely switch to it, or they have to have capital investment to put in extra silos for materials. And concrete plants often don't have the extra bins for additional aggregate sizes to allow them to optimize the gradations. Even though they could save 10 or 15% of their cement, it requires some capital. Now, some of the modern plants in urban areas have these facilities, but often the rural plants don't. So in summary, we can do a bunch of things to reduce the CO2 footprint of concrete. We can reduce the paste fraction by optimizing aggregate gradations. We can even consider adding microfine fillers to extend those gradations. We can reduce the cement clinker component of the paste fraction by adding underground limestone to the cement and adding a supplementary cementitious materials. And that net result will be up in higher strength, lower permeability, lower shrinkage, and improved sustainability. In North America, I said we're using 15% limestone, which is 10% reduction in CO2 over previous cement. And depending on the percentage of SCMs, 20 to 50%, you'll save 20 or 50% CO2. We allow new SCM sources that are, as the supply becomes limited on some things like traditional fly ash, harvested ash, ground glass pozzolans, natural pozzolans. And you can save 8 to 15% of cement just by optimizing aggregate gradations. And some state DOTs will require that now. The standards all allow all the different chemical admixtures, including special purpose admixtures. And we need to further develop performance specifications. One last thing I just want to mention, the bottom bullet there. The wireless in situ sensors are really cheap now, and people are adopting them on construction sites everywhere. And it allows people to understand through the temperature and time curve maturity, estimate the strength of their concrete in situ, and not rely on cylinders and cubes in the laboratory at constant temperature. Because typically in the structure, unless you've got very thin slabs, the concrete's going to get stronger faster than indicated by the lab tests, which means contractors have adopted this technology because it allows them to accelerate construction. And that's money. In summary, Portland-based cements will continue to be used for most concrete applications. They won't be replaced by weird and wonderful materials, but we can still reduce the carbon footprint of those concretes using tools we have today, doing the things I've talked about, optimizing aggregate gradations, using SCMs, using limestone. The national standards already allow the use of these materials and methods. We just need to get past the barriers along the construction chain to change the whole, to get past these barriers. So thanks very much for listening, and I hope that was interesting, and I'll be happy to answer questions.